Welcome back. We're going to begin our work on Unit 3 for Math 109. Both Unit 3 and Unit 4 consider content taken from Chapter 3 of your textbook. Before we get into the PowerPoint, I'm going to tell you that I've made an executive decision that we're not going to look at material from Section 3.1. 3.1 looks at different base number systems, different kinds of numeric systems like Roman numerals. And I don't mean to tell you that they don't have merit and they're not worth considering. I just don't know how pertinent that they are in an elementary math classroom. So we're going to pass on that, and we're going to spend some time on methods and strategies for helping kids be more adept at doing adding and subtracting. And then in Unit 4, we'll switch our focus to multiplying and dividing. So let's go ahead and fire up a PowerPoint here. Hold on tight. Let's see if we can find this thing. That looks like it. All right. Let's go from the beginning. Click again. There we go. All right, so you can see we're going to look at sections 3.2 and 3.3. We'll split out Unit 4. We'll take a look at 3.4 and 3.5. All right, so you've already kind of heard this from yours truly. We're just going to pass on section 3.1. You certainly are invited to read it at your leisure. There are useful things in there. I just don't know that, if we complain about how kids don't master basic number skills, I don't know that we pull our focus away from the mastery of those number skills and say, well, why don't we take a look at Roman numerals? I don't know if you remember Roman numerals, but I can't remember having done much with them other than convert them to Arabic and back and forth. So we're going to pass on 3.1. All right, there's a good look at what's going to happen. Remember, as you introduce the idea of doing operations with young students, the important thing is you don't just show them how to do the algorithm. Unfortunately, that's how I was taught math, and maybe some of you were taught math. But I think we've come a long way in the teaching of this subject in that we want kids now to know why it works. We want kids to be able to touch, to hold it, to move it. The use of manipulatives is significant as we introduce these concepts of adding and subtracting. So I behoove all of you, when you are in that classroom and those kids are yours, you're going to have to make a call in terms of when to put the manipulatives away. Don't put them away too quickly. All right, don't transition over to that pencil and paper before everybody in the room seems to be ready for it. And quite frankly, I don't know that it's a universal. I don't think you can say, all right, well, it's Tuesday now, we're putting all the manipulatives away. I think it's possible that Timmy might need manipulatives until Wednesday or Thursday. All right, there we go. Objectives, again, you already know that I get annoyed when people read slides to me, so I'll leave them up there for you to look at. Lots of different things for us to look at in terms of different ways to approach the ideas of adding and subtracting. All right, welcome to section 3.2. You and I will now begin adding. Well, we've already talked about the natural numbers. Some of you might have heard these called the counting numbers, because when you count items, you start with 1. You don't start with 0. So that is the natural numbers, and we've met this set before. If you want, you can also call it the counting numbers. If by chance we add 0 to that set, we create a new set, and that set is considered to be the whole numbers. And the way you teach kids to remember that, 0 looks like a whole. So it's in the whole numbers, but it's not, it's not in the natural numbers. Okay, how do kids learn to add? Well, if you ever watched two little kids add some items together, you put some in the first pile and some in the second pile, what they'll do is they'll actually pick the items up kind of one at a time and count them. 1, 2, 3, 4, and then they'll move to the next pile and they'll continue counting. And your author says, let's call that counting on. So what he does is he counts the number of items in the first pile, and then he continues counting onward from where that number left off. And that's the introduction for most kids to the process of addition. They actually count the items, and it's fine as long as it's a relatively small number of items. Kids aren't going to get too deterred. Obviously, if you got a pile with 6,307 items and another pile with 3,208 items, the kid's going to get a little hypertensed. But that's counting on, and it's really how most of us have our first experiences with the idea of adding. All right, now I kind of like this and I kind of don't like this. Your author gets into this set business. So he's got two sets there, and this is his counting on extension. So if you were counting the blocks in circle A, you would say 1, 2, 3, 4, and then you would continue counting on as you picked up counting the blocks that are in set B. And you would say 5, 6, 7, And you would say, holy cow, I got 7 blocks. And if you put them all in a big pile, which you kind of see on the bottom, that's what you would have. And that's the cumulative set. There would be 7 items. So if you are now looking back and saying, dang, that looks a lot like cardinality, it kind of does. How many items are in each of the 2 sets? If you put them together, the cardinality of the resulting set would be the sum of the numbers of items that were in the 2 component sets A and B. It's important to point out that the 2 sets A and B have to be disjoint in that they have no items in common. All right. And that's just a really nice way for us to look at. Now, frankly, I think if you did set notation with a second or a third grader, it could go badly. So I don't know that this is maybe the best way for us to get into it. I certainly like the counting on idea. Having the kid get in there and actually count the objects, I think is worthwhile. All right. Terminology, you probably know that when we add, we find the sum. And the things that we're adding, the numbers that we're adding, are called the addends. And again, that's math words that sound impressive. I don't know that it's worth having kids memorize them. I do think it's important kids know that sum is associated with the process of addition. I don't know that they need to know that those things that have been added are the addends. All right, here's another model for adding. It's using a number line. So what we're going to do is we're going to draw a number line. Now, if you're the teacher, you can prepare these number lines ahead. And you can see, you say, all right, here's where 0 lives. And you come to the right in some place, you locate a place and you're going to call it 1. And then you just replicate that distance as you move to the right and you show where 2, 3, and 4 are. Again, no negatives so far, so you don't need to have anything to the left of 0. And we're going to use the idea of adding with our number line. And what we'll do is we'll draw arrows. If you remember from science class in high school, you might have heard them called vectors. So we're going to draw an arrow that starts at 0 and ends its displacement at what that first number is. And then we'll add by starting a second arrow where that first arrow ended and running its displacement to the right. And then we'll try to figure out, well, where would the component arrow be if it covered both of those displacements. Here's an example, and both of these are the same numeric problems. You know, Carla's got ribbon, she's got 4 feet, and then she's got 3 feet. The question says, how much ribbon does she have? So there's the visual. You can see that we have 0 located. We've located a convenient scale for 1, and then we've replicated to show where 2 and 3 and 4 and 5 and so on are. The first arrow starts at 0 and goes to the right as far as 4, and then the second arrow begins its journey where the first arrow ended, which is at 4, and traverses 3 units to the right. And you say, holy smoke, it looks like we're at 7. And that's the resultant there in red. So that's using the number line model as a tool for adding. I like it. Again, if you got big numbers, it's a little bit more clunky. But if you got relatively small numbers to add, it's a good visual for the kids. They can see it, they can count it, they can hold it. If you don't want to do all the arrows, you can have kids do jumps. Kids do really kind of like frogs. So again, you probably want to prepare the number lines ahead of time, and you can have the kids do the frog thing, hop, 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 and wherever he ends his first numeric, he'll start hopping again to show his second numeric, and the sum is at the end. Okay, so number line models for addition. There we go. At this point in time, we discussed with the kids that some numbers are bigger than others, and that means some numbers are smaller than others. And the number line is useful in that sense because when we look at numbers on a number line, numbers that are farther to the left are less than numbers that are farther to the right. So you can attach some kind of a meaning, a visual meaning with a number line, comparing sizes of numbers. So if it's to the left on the number line, it is less than something that is to the right. The technical definition says if it's less, there's some number that you could add to the little guy that would get you up to match the amount of the big guy. So there is some positive number K that if you added it to A, you would be able to match the value of B. Some other inequality signs that you have certainly seen: greater than or equal to, less than or equal to. I'm a little sad that sometimes kids can't read them. The old adage is, the alligator eats the bigger number. I think a lot of kids have heard that. So I look, if it's what works, it's what works. I kind of wish in my utopian world the kids could just know which symbol is which. And that, my friends, will shut down video 1 for Unit 3. We'll be back in a bit with video 2. See you then.